Hi, it's Dr. Khan with the last section from Chapter 4. You're almost there, 4:7 to 4:10. We're going to talk about why some plates are increasing in size while some plates are decreasing in size. We'll want to know which ones are which. The most important section from this video is going to be section 4.8 that lists and explains the support or evidence that we have for the theory of plate tectonics. We'll talk about how we measure plate movement, and then in section 410, we'll talk about how or why plates move, our leading ideas about how that actually takes place. So in 4.7, you should know that plates and plate boundaries will move and are created and destroyed over time. So even boundaries between two plates are destroyed and created over time. Our best example of that is the breakup of Pangaea that started about 200 million years ago, where the continents we envision as being together, right, fitting together like puzzle pieces. That was Alfred Wegener's idea as the continental drift hypothesis. But now we have this theory of plate tectonics. We have a better understanding of the mechanisms for how this might happen and why. So the breakup of Pangaea actually opened an ocean basin as those continents started moving apart from each other. We have a divergent plate boundary. And that divergent plate boundary created the Atlantic Ocean. On the other side of the globe, we have the Pacific Ocean, where we have subduction zones where that crust is being recycled and pulled back into the mantle. So all around the Pacific Ocean, we're getting smaller. We're subducting that ocean crust. So over time, again, the Atlantic Ocean recently has been getting bigger since its formation during the breakup of Pangaea. And then over time, and then moving forward into the future, we'll have a shrinking of the Pacific Ocean. The breakup of Pangaea is shown in figure 4.22. So here we see the continents together. Green is North America, pink is Eurasia, so that's Europe and Asia, moving apart, moving apart, moving apart. We see this opening of the Atlantic Ocean, and now we have evidence of that mid-Atlantic ridge that's running between these sets of continents, and that's continuing to spread out and move those continents away from each other. So over time, North America is continuing to move away from Europe, and South America is continuing to move away from Africa. Our best evidence and earliest evidence came from ocean drilling, our ability to drill into the sediments of the ocean floor and examine those and use dating techniques in order to figure out the age of those sediments and estimate the thickness of those sediments as well. So here we see a picture of a mid-ocean ridge. You can imagine this as the Atlantic Ocean. So we see the mid-Atlantic ridge here, and we have ships that are drilling into the sediment and collecting these sediment cores. One trend that we see in this image is that as we move away from the center of spreading, so we move away, so we're getting older as we move farther away from the center of spreading. That's one trend that we see. So younger rocks are nearer to this ridge where new crust is forming, and as we move further away, they get older on both sides. And those ships that are drilling into the sediment are also showing that the sediment itself is deeper in areas that are older. And our reasoning here is because as we get further away, more time has passed and more sediment has been able to accumulate. Basically, this rock has been around longer, so it's been accumulating sediment for a longer period of time. We also have evidence in our hotspots. A hotspot is this rising bubble or plume of mantle material, so molten rock. And it's kind of a plume that comes into the crust and then forms volcanoes. What's interesting is that plume of mantle material is relatively fixed. That's mantle material, but the crust moves along on top of it. So think about the mantle or hotspot as a fixed spot, and the crust is moving along over it. The best example, the most visible example we have of that is the Hawaiian Island chain, although we do have examples of this happening on the continents as well, which we'll talk more about when we talk about volcanoes, Yellowstone being a great example of hotspots occurring on a continent. But the idea here is that these hotspots form a track and then consequently a chain of volcanoes. For Hawaii, it's the chain of volcanic islands. If we take a look at the Hawaiian Islands, this is the big island here. This is the island where we have active volcanoes occurring. And although we're just seeing the tips of these are actually mountains that are underwater and have accumulated enough volcanic rock that they're actually poking out of the ocean. So these are huge mountains that are underneath here that have formed from volcanic eruptions over a hotspot. We see that we have these smaller islands out here and then the large island here. Again, this is where volcanoes are actively erupting. This larger island is around here with those smaller islands trailing behind it. But if we keep going, we see seamounts. Seamounts are volcanoes that no longer peak above the surface of the ocean. So the mountains are still there, they're just not above the ocean. The reason is because they're older and they've been eroded down where they're now sitting below the surface of the water. What this is showing you here, this hotspot track is showing you that over time, this location of the hotspot hasn't moved, but the plate has dragged over this hotspot, creating new volcanoes as it goes along. So if we take a look here, this is kind of counterintuitive for some students when thinking about this, but the plate is actually moving in this direction. It's moving in this direction. And if we think about where the next volcano is going to be, it's going to be out in front of the current big island. And that's because, again, with the crust moving in this direction, the ocean floor that's now somewhere around here is going to be moving over that hot spot next. So it's this general direction. Another line of evidence is paleo, meaning old, magnetism. So this is something that's interesting. We have this rock record of our magnetic field, of the Earth's magnetic field. So we think about like a bar magnet having a north and a south side, the N and the S on a bar magnet. That's sort of how we think about the Earth as having like this bar magnet that runs through it, giving us our magnetic field. What's interesting is as igneous rocks form from magma that cools, if those igneous rocks have a lot of iron in them, those iron minerals tend to align according to the magnetic field. So we have some kind of record about what the magnetic field was like, its direction and intensity. So what we look at in the rock record is something interesting that's happening. So first of all, where is north? Where is magnetic north? You should know that the pole, the North Pole, does wander a bit and sometimes even flips completely over geologic time. So sometimes we see what was the North Pole magnetically flips to the south and magnetically will flip back to the north. That's happened several times in geologic history. We can see that in the rock record. But with that polar wandering, with where is the North Pole? Well, it's moving slightly over time. It really doesn't make sense if we look at rocks in Europe compared to rocks in North America. It looks like the North Pole was in two different places. But this can be explained by plate tectonics. If we put the continents back together during, around 200 million years ago, for example, when Pangea was just starting to break up, if we move those continents back to those positions where we now understand those continents were located, those lines now line up. And that's what image B is showing us, that it actually makes sense that all of the rocks are pointing to the correct North Pole at the time if we put the continents back together to where they were at the time of formation. And again, with these magnetic reversals, there's a smart figure video that I encourage you to pause this video to watch. But what we're seeing is over time, this volcano keeps erupting and erupting and erupting. And we have this rock record of where north was from our rocks that contain iron. So looking at this, we can actually see the normal north-south alignment. But if we go back further in time, we dig deeper through the igneous layers, we actually can see that reversal of the pole, and we go back again and it reverses, and again it reverses a fourth time here. So some of these volcanoes just give us a really great record in the lava flows that have hardened over time of where or which direction that the north and south poles were. So how's plate motion measured? So we do have our ocean drilling ships that take seafloor samples, and we're able to approximate dates by examining those sediments. We have our paleomagnetism. We have that rock record as well. We also use space age technology currently, like GPS technology, I think is the one that's easiest to understand. Some of the plates are moving so rapidly that from the time that GPS was invented to present day, the plates have moved significantly enough that the GPS software has to be updated to show the new location. So all the streets were off a little bit. This is most noticeable, I believe, in Australia, where they've had to update and shift everything because that continent is moving quickly compared to when that GPS data was first loaded. So we can use that GPS data to approximate maybe it's only a few centimeters per year, but that adds up over time. So now we have an idea that not only do plates move, they don't move at the same rate. So we have this North American plate that's moving away from the Eurasian plate. The North American plate is moving at about the same rate as your fingernails grow. So it's not a lot on an annual basis, but it does add up over the millions and then billions of years of Earth's history. So we don't have a fabulous model yet that totally explains the mechanisms of plate tectonics, the why or the driving forces. But we do understand that the mantle is likely driven by convection currents. So we have this warmer core of the Earth that's a lot hotter. The mantle is then warmed by that core, and that warm mantle material will expand to become less dense than the material around it, which forces it to rise. Where it's cooler, and as it cools, it becomes more dense and sinks, and that's what a convection current is. And we can kind of model this or see this in a cooking pot of water, where the heat source is from below, and as that water is heated, it will rise. It's colder comparatively at the top, becomes more dense and sinks again. That's a convection current. So we understand that that's likely happening in the mantle, and that's likely driving the motion that we see with the lithospheric plates. Remember lithosphere, that rigid part of the Earth's surface where it's going to kind of ride over those mantle currents. There's two dominant forces that we think act upon those lithospheric plates. So first of all, a force called slab pull. So as a slab is being subducted, oceanic in this case, being subducted under a continent, that sinking of that colder, denser oceanic crust pulls down the crust behind it. So that's a driving factor of plate tectonics. And ridge push is thought to be a result of gravity kind of pulling downwards on this elevated ridge that's kind of sitting up higher than the rest of the rock material. As for the rest of 4.10, I do believe it goes into two models of mantle convection, and I don't need you to know that. That will not be testable. But you should know these two terms here, slab pull and ridge push, as our best model or understanding of the forces that act on those lithospheric plates. That's it for chapter 4, and that's all of the content for the first week. So now you'll be doing your notes and then the Pearson for this to review. Let me know if you have any questions.